Good afternoon, everyone. My name is Gabriel Moreno. I'm a principal researcher here at the SCI, and I'm the last speaker between you and the reception. So in this talk, I'm going to tell you about work we are doing for assuring large-scale systems. This is a two-year project. We have concluded the first year, in which we have developed the foundations for the work, and that is what I'm going to present. And in the second year that we just started, we are working on developing tooling and some enhancements so that the work is more practical. So the motivation for this work is that delivering capability at speed and scale is a top priority for DoD. Now, the systems that deliver that capability, they need to be assured, and that becomes the bottleneck to achieving that speed, because sometimes assurance slows down the process. So what we are doing is developing an approach to overcome some of the barriers that slow down assurance. So I'll start with a high-level overview, and then we'll go into a few more details. I'm going to use this simple drone example throughout the presentation. It's an autonomous drone that has to carry out a humanitarian mission, fly to the destination, and when it gets there, drop these life-saving supplies. On the right there, you see an architecture of the drone. It's built out of different subsystems. Some of them could have been reused from other platforms. In the drone itself, there's a mission manager that orchestrates the work of all the other subsystems. There's that guidance subsystem that does the waypoint navigation. And what it does is compute what we call reference points, which are like waypoints, but a much higher density. And those reference points are sent to the flight controller. The flight controller takes care about the flight dynamics to make sure that the drone goes from reference point to reference point. And then there's that payload controller that is the one that is in charge of the release mechanism for the supplies. So again, the problem is that assuring these systems is a bottleneck, and there are different factors that contribute to that. Some of them are here. One of them is that it's difficult to reuse assurance results. So if we are reusing a system or a subsystem that was already assured, it's difficult to reuse those results. There's difficulty to integrate analysis of different types from different analysis domains. Also, there's no notion of different trust levels. And when we talk about different analysis, they will give us guarantees with different levels of trust. And also, there's assurance interdependence between the subsystems. So a system, when it was assured, may have made an assumption on something that comes from another subsystem, and that is usually not explicitly stated. So we're trying to address those barriers. Now, when talking about analysis, we can think of two sort of like levels of analysis. On the one hand, here on the left, we have domain-specific analysis. These are like timing analysis, safety analysis, security, and so on. They rely on different artifacts, from source code or binary code to models that are specific for the analysis that are done. And also they use different analysis mechanisms. For example, starting from human inspection, which we consider an analysis as well, to testing, simulation, and model checking. Now, the other level is the composition of those analyses. And that is at the level we work in this project. So the idea there is to integrate the result from diverse analyses that we are using, and integrate the results for different subsystems. So not only different kinds of analysis, but different parts of the system. And we want to check the logical consistency of that integration, and also determine the trust level of the result we get at the end based on the trust levels of the things that we are composing. So to compose this analysis, we have to follow a few steps. First, we have to identify the analysis that we are putting together. And for each of them, we have to do a few things. We have to identify the assumptions that the analysis makes. This is critical to do then the composition in a sound way. Then we have to be specific about the guarantee that the analysis provides. And even if a human is doing the analysis, let's say it's human inspection, for the formality of the model, we want to specify what is that analysis is guaranteeing. And also we have to identify all the resources that affect the analysis. So by resources, we mean all the factors that would affect the result of the analysis if they change. It could be inputs, configurations, things like that. And then, based on those resources and the values that they cover, with that we define the level of trust. We use a specific concept of trust that I'm going to explain in a few slides. Then we have to make sure that all the analysis assumptions are satisfied, either by the results of other analysis or by axioms, let's say, evidence that we have. And then we want to make sure that there are no logical inconsistencies. So if a subsystem assumed something when it was analyzed, then that cannot be inconsistent with another assumption made somewhere else in the system. So at a very high level, the solution approach that we've taken uses a new artifact that we call the argument architecture. And then we use logical judgments to hide the details of the analysis. And these logical judgments are sort of like the first class components in that argument architecture. We introduce a formal definition of levels of trust, and we automate the analysis of the composition once we have the argument architecture put together. So now let's start looking at a bit of the details for this. So the argument architecture is analogous to a software architecture, but for argumentation about and assurance the system. So instead of being the set of components like in a software architecture, it's a set of arguments that are needed to reason about the system. And the elements, like I said before, are these judgments that encapsulate the domain-specific analysis and the logical connectives that connect those results. And with the argument architecture, we can see how guarantees from one analysis satisfy the assumptions of other analysis, and also we can see how trust flows from assumptions through analysis and to guarantees. So I've been talking about the judgment, and this is a concept that comes from logic. We use this visual way to depict a single judgment. It's the first class component in the argument architecture, and it's based on three things. The analysis, that is the one that is giving us the guarantee, and also the assumptions that the analysis relies on. And in addition to that, we have these trust levels. Now, in logic, a judgment is a declaration that some proposition is true. So in this case, we use a judgment to express the fact that some analysis was done, and it has shown that guarantee holds given the assumptions that were made. Now, I've mentioned trust levels. There are different factors that affect the trust we have in the results of an analysis. Trust depends on the rigor of the analysis method that we use, on the fidelity of the models that we use, and also on the coverage of the analysis. In this work, we focus on the coverage of the analysis to define the trust level. And like I said before, we use this concept of resources, and the number of, let's say, situations or test cases that have been covered by the analysis, they correlate to the level of trust we have. So you can think the more situations that the analysis has considered, the higher trust we have in the result. So the trust level qualifies the guarantee in terms of the context under which the assumption has been shown to be true. Now, to use this concept in our logic system, we have to formalize it. A single situation or a test case that is covered by an analysis is a function that assigns values to resources. So if you think of a component where the resources, the thing that matters and could affect the result of the analysis, let's say are velocity and altitude, then a single test case or situation is a function that assigns a value to each of those resources. And the trust level is defined by a set of those functions. And you can think of that being the set of all the situations that the analysis covers. With that, we can define a partial order between trust levels. If we look at the pictures here at the bottom, we use the square subset to indicate the relationship between trust levels in terms of ordering. And the one on the left says that T1 is a higher trust level than T2. Why? If you look at the picture, it covers a larger space of situations that the analysis has considered, therefore we have higher trust. Now, there are trust levels which are not comparable, like T1 and T2 on the right. We cannot compare them in between them, but we can say that the intersection of them is it's a lower level of trust than both T1 and T2. So in logic, I mentioned this concept of a judgment. There in the center of the slide, there's the formal expression of a judgment. And to the left of the turnstile symbol, we have gamma, which is the set of assumptions. And then on the right, we have the guarantee. And the judgment expresses that if those assumptions are satisfied, then there's a proof that the guarantee holds. Now, in our work, we want to include trust levels to this reasoning. So we add a few things to the notion of a judgment. We added a label, A, that basically it's just a label, but describes the analysis that was done. The component to which the guarantee applies, and then that at T is the trust level with which that guarantee is provided. So let's look at an example. Suppose we have an analysis that has shown that the output of the flight controller that I mentioned before is safe, according to some definition of safe. On the curly braces at the end, you can see the trust level. That is the context under which this was shown to be true. And in this case, it was for altitudes higher than 200. But then the other important thing is the assumption. So the assumption here was that the reference points that I mentioned before are provided to the flight controller with a frequency of at least 5 Hertz. So we have the expression here, not only of the guarantee that the analysis provided, but also what assumption was made when that was done. One more thing, we want to be able to propagate trust throughout the architecture and throughout this judgment. So we add this variable or placeholder T in the assumption so that then we can propagate trust, because obviously the trust we have on a guarantee will depend on the trust we have on the guarantee that satisfies the assumption. And we'll see an example in a second. So now that we have these elements, let's see how we use them and how we compose judgments. So here's the same judgment we had before. That was for the flight controller, and we know it's safe only if that assumption of reference points being sent at 5 Hertz is satisfied. So now we need to satisfy that assumption, and to do that, we bring another judgment that gets composed, and this is a different analysis, timing analysis in this case, and for a different subsystem for guidance. The timing analysis, under some assumptions about the CPU utilization on that processor, guarantees that the reference points are going to be sent at that frequency of at least 5 Hertz. And that is done with some trust level that is different from the trust level we had in the assumption. Now, this is a visual representation, but behind that, we have the logic reasoning and inference rules that support all that, and with that we can make sure that this composition is sound. We are not going to spend time reading the details, but one thing that I want to highlight is that trust levels at the far right of the inference rule are explicit in the logic. And in this case, it's saying that the assumption we have has to be guaranteed at least with that trust level that we assume. So we can look at this from different angles. We can say, okay, if we assume that the trust level was T, we need to have at least higher than that on the guarantee that satisfies that assumption. But on the other hand, we can do a different thing and say, well, this is the trust level we have in the assumption. The trust level of for the guarantee will be something that we can compute depending on that. Now let's look at another example. In this case, it's for the same subsystem. We are now composing two different analyses. We have the timing analysis for the frequency of the reference points, and now we have another analysis that was based on testing that guarantees that the distance between reference points is going to be no more than 10. And we want to compose them now and say that the guidance component satisfies those two guarantees simultaneously. And the question now is, what is the trust level that we can have on that guarantee based on the things we are composing? And again, we have our logic behind that. The lowest inference rule, the one that allows us to do that conjunction, requires that the two things that we are conjuncting are at the same trust level. But now here, notice that the two analyses that we were composing had different trust levels. So we have to make them equal. And the way we do that is by downgrading the higher level of trust to the lowest level of trust so that we can compose them. So that allows us to make a sound composition of the results. But on the other hand, this is useful because it will show us in the argument architecture where we had to downgrade trust to be able to compose it. So it could help us to determine where to allocate assurance efforts to, let's say, prevent downgrading trust when we have higher trust that we could use. So putting all these things together, we can have an argument architecture where we have different analysis results that have been composed for different systems. And with that, we can check and make sure that there are no unsatisfied assumptions or mismatch assumptions, that there are no logical inconsistencies, and we can use the levels of trust and compute what is the trust we have on the different guarantees that we are providing. So when I started, I mentioned these 4 barriers. So let's go back to that and see how the different pieces address them. So one was the lack of effective reuse of assurance results. We use this notion of judgments to encapsulate the results, providing a clear composition interface so that then we can reuse those assurance results. The other one was the inability to integrate analysis of different kinds. And we saw how with the notion of a judgment that hides all the details of the analysis but exposes the things that the analysis depends on, we can compose analysis of different kinds. The other one was that there was no notion of level of trust, and you saw how trust is explicit now in the logic that we have that allows us to do this relay guarantee reasoning with levels of trust. And the other one was the interdependence between subsystems. And you saw an example where one subsystem, the assurance for one subsystem, had an assumption, but now that assumption is explicit, and how we satisfy that assumption is also explicit. So to wrap up, we presented this approach for assurance, which allows us to do incremental and compositional assurance with this explicit consideration of trust. We are starting to develop tools to make this approach practical. And in general, we believe that the co-evolution of the system architecture with the argument architecture will be useful to develop complex systems that can be assured in reasonable amount of time. So we are interested in working with you. So if you have systems where you think that this approach would be applicable, If it's a system that has already been assured, but it's evolving and you want to reuse the results, we will be very interested in hearing from you. So please reach out. This is a team effort, so both SCI staff and our academic collaborators. And thank you for your attention.